Hello everyone, my name is Neha Manohar and I'm a React Fellow in Act 1, and today I'm going to talk to you guys about solvent-driven infiltration of polymer into nanoparticle packings in order to make nanocomposites. So really quickly, to give you guys a more broad motivation, up to 15% of total US energy usage comes from chemical separations, industrial chemical separations. And a lot of this comes from conventional separations methods like distillation. And it's hypothesized that up to 90% of the energy load associated with distillations for separations can be reduced by using membranes instead. So there's this great need to really introduce efficient and scalable membrane technology for industrial applications. So really quickly, conventional membrane technology has this drawback, this trade-off between permeability and selectivity. So basically, as you increase the purity of a permeate going through a membrane, you get less throughput, or you get less flow through it. So there tends to be this conventional upper bound in both gas separations and water purification that we would really like to drive up. And previous studies have shown that incorporating nanocomposites into the selective layer of a membrane can really drive up this perm selectivity of your membrane. So an example is the study that looked at increasing amounts of nanoparticle filler, increasing amounts of nanoparticle filler into a polymeric membrane. And what they found that as they increased how much volume fraction of nanoparticle they had in their membrane, they could drive up the permeability without significantly hindering their selectivity. And this is really promising. However, there are some limitations in making these nanocomposites, because in this study they used physical mixing, and they found that they reached a certain limit in how much filler they could actually incorporate. And what we really want is to follow this trend and maybe see if we can go to higher filler fractions and drive this trend further and make even more efficient membrane filtration technology. So we want a more scalable approach. Previously in our group, we have been able to circumvent this physical mixing fabrication methodology by coating this bilayer. So basically we start off with a substrate, on top we coat a polymer, and on top of that we coat a nanoparticle thin film. And here we just thermally anneal it, and we're able to see that the polymer infiltrates into the void spaces between the nanoparticle packing, a lot like you would imagine a fluid going into the pores inside of a sponge. And this really makes a very high filler fraction nanocomposite in the end. However, I jumped the gun a bit earlier, but this still requires heating, and it's still a little energy intensive. And conventional separation membrane polymers can have very high TGs as they're very glassy. And this could mean that you have to heat them to quite high temperatures in order to get this softening effect, to drive them into these nanoparticle voids. So what we'd like, ideally, to reduce this energy cost is to have a room temperature alternative method that still circumvents the need for physical mixing. So what my project entails, where I come in, is we have the same bilayer setup. We have these nanoparticles coated on a polymer film, and we expose it to solvent vapor. So we do solvent annealing instead of thermal annealing. And what happens when you expose this really high curvature, because these are 20 nanometer diameter nanoparticles, when you introduce this really high curvature environment to the solvent vapor, they want to condense by this phenomenon called capillary condensation. So basically the high negative curvature of the fluid interface leads to this stabilized liquid condensate phase that makes the nanoparticle layer flood with liquid solvent. So what happens then is we hope that we can induce the polymer to infiltrate just by an entropy of mixing driving force. And you can see here's the really high negative curvature of this fluid interface that leads to the stabilized liquid state. So in my system, if you look at it, the length scales of my polymer in the solvent phase in the dissolved state are actually very comparable to the void spaces between my nanoparticles. So this is a very highly confined system. And if you look at, I used 3 different molecular weights of polymers, you can see that the size scaling of the radius of gyration is quite comparable to the average void fraction in my nanoparticle packing. So we really have a very interesting, we need quite a high driving force in order to drive this polymer into the system, and we're hoping that mixing with the solvent or solvation will drive the polymer to infiltrate. And I'm going to focus today on the 8K, so this low molecular weight system, but I can tell you that I've observed infiltration with all of these molecular weights, so even for the higher molecular weight. So how we study this, I think it's on autoplay or something. But how we study this system is using ellipsometry measurements before and after infiltration. So basically you can get refractive index and thickness values for the bilayer before infiltration, and then you can compare that to the refractive index and thicknesses of the layers after infiltration. So what you see is a decrease in the polymer layer thickness and an increase in the refractive index of the nanoparticle layer thickness, indicating that some of the polymer has left the bottom layer and infiltrated into the nanoparticle packing. And you can use conservation of polymer volume to calculate what the volume fraction of polymer is in your nanoparticle layer after infiltration. So the setup that I use, I'll just go back so this gives me a little bit more time. There we go. All right, so the setup that I use is a controlled vapor flow setup where I have a nitrogen tank going into a mass flow controller that goes into my solvent bubbler and basically sends a controlled activity stream of my solvent into my chamber. And I can observe this via in situ spectroscopic ellipsometry, so I can actually see the dynamics of the infiltration as it's occurring. And then I also have this purge stream incorporated, so I can immediately quench my my infiltration as it's occurring. So before I started my infiltration experiments, I wanted to do a quick sanity check to see if this capillary condensation phenomena actually occurs. So what I did was, instead of having this bilayer, I just had nanoparticles on my substrate, and I exposed it to solvent vapor. So here I have two different samples, one that's been purged with nitrogen and one that hasn't been purged with nitrogen prior to my experiment. And this difference in refractive index initially basically indicates that in ambient conditions I have humidity and therefore water condensing into my pores. So however, when I expose both of these samples to solvent, what I see is that they reach the same refractive index, indicating that both have a similar level of solvent condensed into my nanoparticle packing. And this refractive index change actually indicates that my film is fully flooded with solvent. So I do get my nanoparticles are small enough that I can actually induce full flooding of my nanoparticle layer with solvent. And when I quench the system, basically by again purging it with nitrogen, I find that it reversibly goes back to the original refractive index. And this kind of is a sanity check in that any irreversible change I observe in my system, in the bilayer system, is probably due to polymer infiltrating and not just remnant solvent or other things condensing in my nanoparticles. So I tried this with many different solvents, and I've characterized the different solvents using a chi parameter, where this is basically my poor solvent regime, and this is good solvent. So here the solvent quality is decreasing as you go down the x-axis, and this is the volume fraction of polystyrene I have in my nanoparticle packing. And basically, I see that there's a decreasing trend as I decrease solvent quality, which is kind of what we expect. And I can achieve, so my void fraction is roughly around 0.35, and within 30 minutes I can achieve pretty high filling of these nanoparticle packings with polymer. Now, the reason why I don't run it for much longer is that, for one, these seem to occur within 5 minutes in the really good solvent systems. However, I also observe some de-wetting. So there's some instability of my films given long enough exposure times in the good solvent regime. However, for my poorer solvents, this 0.5 case and this 0.78 case, I can run it for longer, and I see that unexpectedly, even with the poor solvent case, I get infiltration given enough time. So this indicates to me that either there's some inherent property in the polymer solution solvent system that slows this process down, or there's a different regime, maybe a surface-driven regime, that leads to infiltration in this case versus these cases. So this was really exciting and interesting because we expected this to occur. We weren't sure that this would occur. So what we thought was we could maybe exploit this in some way to make the system even more interesting. So basically, if you can imagine, rather than solvent annealing, it would be great if we could just directly dunk these films and have them infiltrate. And the problem with this area over here is that it completely de-wets. My polymer completely leaves my substrate if I dunk them directly into liquid solvent. However, with a poor enough solvent, I can actually directly dunk it, for lack of a better term. And what I see is that infiltration occurs, given enough time, with direct liquid annealing of these systems. And this is compared to the vapor annealing. The open circles are vapor annealing, and then the closed ones are just direct dunking of my films, my bilayers, into my liquid solvent. And you can imagine that this is very advantageous going back to the scalability issue of making these nanocomposite membranes, because there already exist industrial techniques for dip coating, especially for membrane applications. So this seems like a more industrially viable route for making these nanocomposites with very high filler fraction. So to kind of summarize, I've been able to develop a room temperature scalable method that can create these high filler fraction nanocomposites potentially for membrane separation applications. And this infiltration appears to be quite robust in that I can use different molecular weights and I can use a range of solvent quality to drive this phenomena. And for future work, I mentioned that there are different mechanistic regimes that might be possible for this. One could be solvation-driven entirely, another could be surface-mediated. So we really want to understand what is driving the polymer to infiltrate in these systems. So one thing that we're doing in collaboration with Dr. Riggleman is running simulation studies. And in this simulation, much like our experimental system, we observe swelling initially, and then we see that polymer slowly begins to infiltrate as a front into the nanoparticle packing. And this is very exciting because we can tune the interactions between our different species and see if it's entirely surface mediated or if it's more driven by solvation, and see how the dynamics look for those cases. And we also want to visualize our infiltrated films better and maybe see if they're more mechanically reinforced and do other testings to understand the dynamics of the system. So with that, I'd like to thank my PIs, Dayon Lee and Kate Stebby, and all of our collaborators. And our whole research group, and the funding sources, especially the REACT program, and open the floor for questions. Thank you.
Have you thought about using a random copolymer like styrene acrylonitrile? Because the acrylonitrile will form loops. Like the styrene is still pretty hydrophobic, it's not going to want to wet too much the silica. But the acrylonitrile has a really nice specific interaction with the surface groups. So you get reinforcement of the acrylonitrile monomers attracted to the particles. Then you have the good properties of polystyrene that you want.
Yeah, we've definitely considered looking into polymers that are more hydrophilic and would maybe prefer the surface-mediated pathway more.
But a random copolymer, a few percent acrylonitrile,
so that it has
95% styrene.
That would be really interesting. We haven't tried that, but that's definitely something we could look into.
What is the depth resolution? Can you tell where the polymer is infiltrated and how much, or even vice versa, your solvent annealing, how fast the solvent's penetrating?
So currently with my ellipsometry model, I can't. I actually model them as homogeneous layers. So I don't have a front that I can observe. I instead observe the change in refractive index of the entire layer over time. So it's more of a homogeneous infiltration into the entire packing based on my model currently, which is why we're hoping that we can try different studies like maybe neutron reflectometry at the ILL to better observe this front dynamics if we can probe that.
How thick is the total?
So the thickness that I use is around 500 nanometers total for the entire bilayer.
Any questions? Okay. So you were talking about when you expose it to the solvent, it becomes fully flooded.
Right.
So compared to your schematic where it looked like it was just at the tight spots.
Right, yeah.
You think it's voidless?
We think so, just based on the change in refractive index. It would indicate that the entire void fraction that we have initially occupied by air would have to be replaced by something with the refractive index of the solvent. So based on just the change in refractive index for all of our solvents, we seem to observe that the packings are fully flooded.
So does that insight about it being fully flooded, does that impact how you think about the polymer going into the system?
Definitely, because if it's not fully flooded, we may see the polymer taking more surface-mediated pathways. It would definitely affect the dynamics of the system. I don't know how we can, this is already the lowest flow rate that I can introduce my nitrogen into my solvent bubbler, so I've reached the lowest activity of the system. I could try to lower the activity further and see if I can only get partially flooded, or increase the radius of my nanoparticles.
You can mix two gas lines if you want to further dilute it.
Right.
It's only more plumbing.
Yeah. I actually, if I introduce a mass flow controller into the second line, I could do that. I currently just have an open closed valve, but that's a really great idea.
Talking about de-wetting of this is the de-wetting the polymer from the nanoparticle?
Right.
And why does that happen
So
more when you have a lower current with the solvent?
I'm not entirely. So what I see with the, if you mean the direct dunking.
No,
For just the de-wetting, so it's
de-wetting.
de-wetting of the polymer from the substrate, not from the nanoparticle.
Okay.
So the solvent seems to be replacing the polymer on the substrate, or somehow unstabilizing the film.
And how do you detect that?
So basically, along with these ellipsometry measurements, we get a mean squared error. So that's based on either surface inhomogeneities or inhomogeneities in each film layer. So as you expose it for longer, this mean squared error increases considerably until the model becomes less relevant.
Do you have any optical microscopy that indicates that you might be delaminating from the solid substrate?
I haven't done any microscopy on the delaminated, but that would be an interesting thing to see.
With thermal annealing, we see a lot of cracks.
Yeah, we do see some cracking, but maybe not to the same extent as the thermal annealing.
Any other questions? All right, so let's thank Neha one more time.